Good morning. Okay, so today we are talking about exponential decay. Okay, and we're in algebra, obviously. Okay, so our first thing, in my free time, I performed the bouncing ball lab with a tennis ball to create a table of values below. Okay, so let's do a little review here. This is our first one. So our first review says we are going to calculate the rebound ratio. So remember yesterday from our notes, our rebound ratio was our rebound over our starting height. Okay, how much we rebounded over our starting height. And in this case, if you notice, we're going by 25s at the top and we're going by 15s at the bottom. Okay, so in this case, it won't matter which one you choose. Okay, so I'm just going to choose this guy here. Okay, so my rebound ratio would be my rebound over my starting height. Okay, and if I go do my rebound over my starting height, 75 divided by 125 is 0.6. Now remember, that is an important number in our equation. Remember yesterday we wrote our equation? That is our slope of our line. Okay, that's our m for our y equals mx plus b. Okay, so now it says to create an equation that represents the rebound height at any height. Okay, well, if I look at my table, I also can find my b. My b is 0. So my equation is just y equals 0.6x. Remember, your x is your starting height, your y is your rebound height. Okay? Now, what happens if you don't have your b? You would have to use one of your points to find your b. We were lucky, our table here had our b. Okay, so it says use your equation to predict the height, keyword being here predict, we can't guarantee this, what the rebound height of the ball would be if it was dropped from 20 centimeters. So our rebound height, remember, is our y, and our starting height is our x. So we want to know an x, we want to know what y equals if our x is 200. So I can take this 200 and I can plug it where this x is. So y equals 0.6 times 200. So 0.6 times 200 is 120 centimeters. And there's how far our ball would rebound if we dropped it from 200 centimeters. Okay. Now it says use your equation to predict what the starting height would be for a ball that has a rebound. So this time we're looking for our starting height if we have a rebound of 90. So we're looking for our x if we know our y is 90. I can still use the same equation. So I can say 90 equals 0.6x. And then I ask in this case, how do I solve it? Because x is not by itself. So I can divide by 0.6. I can divide by 0.6. And then I take out my calculadora. 90 divided by 0.6 is 150 equals our x. So it would have to start at 150 centimeters to go up to 90 centimeters as your rebound height. Okay, so the next thing we're going to do is we are going to look at if we let the ball continue to bounce. So yesterday they let it bounce and then they caught it. One bounce. Well, what happens when we continue to bounce? Well, if we were to create a graph of our bouncing, okay, so this is if I were to continue to bounce. It would be dropped, it would hit the ground and come up. It would be dropped and it would just keep getting lower and lower, right? Our little bounces get lower and lower. So we're now going to look at these heights and see what happens with them. You should notice that the graph is a little different. It doesn't seem, it kind of looks like a line, but maybe not, because it seems to be that this first rebound is a little higher than the next one, and then we keep going. Okay. So I did the experiment at home, and this is what I came up with. I came up with the number of bounces, which is our x, and then the height of the ball at that bounce. So instead of just bouncing it once and catching it at different heights, now we're just dropping it from 100 centimeters and letting it continue to bounce and seeing what happens. Okay. Now, at some point, it will reach a height of 0, because at some point it can't bounce anymore. Okay. So let's look at a graph of this. Let's make a graph. So let's say we go, let's see, we can go, the bottoms can go by ones. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That fits. Okay, for our height, we need to go up to at least 100. So 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60, 65, 70, 75, 80. That doesn't work. So 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. That works. 10, 20, 30. Okay, so I'm going to have to go up by 100 by tens. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110. Okay, so we have a graph here. Let's go ahead and graph it. So 0 is at 100. 1 is at 55. 2 is at 30.25. 3 is at 16.64. 4 is at 9.15. 5 is at 5.3. 6 is at 2.7. 7 is at 1.52. And 8 is at 0.084. Well, if I look at this, I see that it does make a pattern. Remember our bunny one? Remember our bunny graph? Our bunny graph went like this. Now this one goes downhill. Okay, so this looks just like our bunny graph. Our graph looks similar to our bunny graph. Okay, except instead of going uphill, it's going downhill. Okay, so remember, in our bunny graphs, we were multiplying by 2 or 4, 3. We were multiplying by the number. So let's see if we can figure out our multiple here. Okay, so I want to know, what do I multiply 100 by to get 55? So 55 divided by 100 is 0.55. Let's do 30. 30.25 to 55 is 0.55. Let's just try one more. We seem to have a pattern. So 16.64 divided by 30.25 is 0.55. So we have now found our pattern. By looking at our graph, we knew it had to be a multiplier. Okay. But in this case, this is called an exponential decay because we are going down. So our new vocab word is called an exponential decay. Okay. So our exponential decay is an exponential function. So remember, exponential functions mean we have a multiplier, but it's an exponential function with a multiplier between 0 and 1. Okay, so notice here our multiplier is 0.55. 0.55 is in between 0 and 1. So that would mean when we did our y equals a times b to the x power, this number here would be a decimal of some kind that is less than 1. Okay, notice I'm not saying negative. Okay, it's between 0 and 1. Our negative sign does something else with our graph. Okay, so you can work on your homework now once you get that done. Have a great day.